and this double compression wave and longitudinal wave. And a compression wave would be like a sound wave, right? Say you have this as a pipe, right? And let's say I take my pipe, right? This is my pipe right here, and I go boom with my hand, right? I have compressed the air, right? And I forced it into the pipe, right? This is how like instruments work, you know what I mean? You have like a flute or something. It compresses the air, and then that compressed air moves because you forced it to, right, with your hand. And if it's an instrument, you do it with your, blowing through the pipe with your mouth, right? And you create these compressions right here that actually move. So these are moving. Those are compression waves, and you can also think of this pipe as your trachea or whatever, not your trachea, whatever, your esophagus, right? And down here you have your, you have your voice box, right? And your larynx or whatever it is vibrates, right? And as it vibrates, the air gets compressed and decompressed, and you get this compression wave. And that's what sound is. It's, it's when you talk, it's because your voice box vibrates, or your larynx or whatever it is in your throat, it vibrates, okay? And that makes the compression wave, okay? And you also have the longitudinal wave, right? You can see this sine wave here. It'd be like if this was a rope, right? And you have two little kids playing rope. One person starts oscillating their hand up and down, up and down, up and down. What happens? You get this longitudinal wave. And I also wanted to bring up about the matter wave, okay? Remember how I was saying, if you have a baseball, it's so big, it's not going to vibrate, you know what I mean? And I was like, well, everything vibrates. Yeah, okay. I did the de Broglie wavelength, right? And this is the formula down here, right? So a baseball, the de Broglie wavelength is 10 to the negative 34 meters, right? Do you know what the Planck distance is 10 to the negative 35, and this is 10 to the negative 34. It's almost at a Planck distance that this baseball vibrates. And you're so big, the baseball's so big, how are you going to see this vibrating when it only vibrates in a distance of 10 to the negative 34 meters? It's not possible. You can't see it. You can't feel it. You can't whatever. You know what I mean? Like I said, all the vibrations from the electrons and the protons and this and that and blah 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 in your all your atoms or whatever, yeah, they all cancel out because they're vibrating this way, this way, this way. They're vibrating in every different way there is, right? But it doesn't all cancel out, right? And this, and overall the baseball, this is what it vibrates, right? Now, the electron de Broglie wavelength is 10 to the negative 10th, right? That's comparable to saying an atom. An atom is like what, 10 to the negative 15th or something like that. So this wavelength for the electron is actually bigger than this wavelength for this baseball, and the reason why is because of the mass. You know what I mean? The more mass you have, the smaller your de Broglie wavelength, and the smaller that is, the smaller you vibrate, right? So the more mass you have, you're barely vibrating. Here you're vibrating, but the distance is a lot giant. It's just a giant compared to this, right? This thing is vibrating big time, right? That's what they mean by matter wave, right? Because this electron, it vibrates. This baseball, it vibrates, right? And if it's moving through space, it's going to create a sine wave, right? The de Broglie wavelength does not say, okay, the electron is a wave and not a particle, okay? It says the electron vibrates and the electron path creates a sine wave. The electron and the baseball, they don't magically turn into some wave function, okay? The wave function is a mathematical construct, okay, that describes this vibration, okay? Just like you have a clock pendulum going back and forth, back and forth. Yeah, a wave equation describes that. It doesn't mean that it's a wave. It's a freaking pendulum, okay? It doesn't turn into some magical thing that we can't see or whatever. It's just described mathematically by a sine wave, okay? It doesn't mean it's a wave. It means that it vibrates, it oscillates, okay? That's what it means, okay? Even though they say that, you know, the electron isn't a particle, it's something in between, something, you know, something new. No. They know it vibrates. Stop acting like morons. If the freaking thing vibrates and it moves through the thing, you can see it makes a sine wave. Don't be idiots. What the hell? That's the thing that kills me. Is that if they didn't know that it vibrated, then I would be like, oh, okay, this is a simple, you know, this is a understandable mistake. But this crap where they know, where 100% of them agree that this freaking electron is vibrating up and down, just like making a wave, and then they act like they're confused. Okay, now you're being a child. You're not even being an adult. I would be ashamed to say that I know an electron vibrates. I know that it makes the sine waves when it moves because it vibrates, but I don't understand. It must be some kind of wave function. Yeah, it is a wave function because it vibrates, you idiot. The path is the wave function, not the electron. Okay, anyways, let me calm down here. You know, thousands of experiments prove that light is a particle, okay? The photoelectric effect is the most common, you know, the most known one of these experiments, of these thousands of experiments, you know what I mean? And all it says is, you know, if you get certain types of metal, shine a light on it, you can see they got red light, blue light, and you will expel electrons, photoelectrons. Why are they called photoelectrons? They're just electrons, but we call them photoelectrons because you just smashed a photon into this and expelled the electron, okay? So the photon electron, you know, the photon part of this word isn't describing the electron as a photon or anything like that. It's just saying that a photon displaced it, okay? So they found out that, you know, photons come in bundles or chunks, right? Which basically one cycle is a photon. Let's face facts, okay? This is a photon right here, right? And if you throw, you know, let's say this metal here, it needs blue light to expel these electrons from this metal, right? But let's say you threw some red light on it, right? But you made the red light so intense, it was so bright that it made the blue light, you can't even see it, okay? And then you'd only shown that red light on there. No electrons will be emitted, okay? Because you need a specific wavelength or a specific frequency, meaning a specific energy, to displace an electron, okay? That, you know, that proves that the photons are coming in at discrete bundles, you know what I mean? Because if not, if it was just a continuous red thing, then if you just gave it a whole bunch of intensity, it should be able to knock an electron off, right? But it don't, because you need a photon to do it, okay? It's kind of like, you know, when you're at the what's it called, the carnival or whatever, or, you know, some kind of amusement park. They got you know, you can throw a ball at something, and it's usually these 3 or 4 or 5 or whatever heavy milk bottle looking things or water bottle looking things, but they're weighted down, you know, down at the bottoms. They got a lot of weight in it, so that it's almost impossible to knock these things over, okay? And then they give you a baseball or whatever. Well, just imagine if they gave you ping pongs. They could give you thousands of ping pongs, and you could throw ping pongs all day. You ain't going to make these things budge, because you need so much, you know, you need at least a baseball to even think about knocking these things over. It's the same over here. You can have as many red things as you want thrown at them. It don't matter. You're not going to expel the electron, because this metal needs blue light, okay? So they say this wave-particle duality, this duality cannot be explained, right? Okay? Really? Why? Why can't it be explained? We know, right, the electron is a particle that vibrates, oscillates, right? Everyone agrees. We know the electron moves, okay? And as it moves, it cuts a path, right? It cuts a path shaped like a sine wave. See this big word here? Wave. See this electron? It vibrates up and down as it moves. And so it cuts out a path shaped like this freaking sine wave, okay? Okay? That doesn't make the electron a wave. It just makes its path a wave, all right? All right? So just the path is the wave. The electron is a particle. And how do we explain this? Right? We explain it with this vibration that we all know about, man. Why do they say it's impossible to visualize duality? Here it is right here. Here it is visualized. I just drew a picture of it. See it? See the picture? You got a particle here. It vibrates, and as it moves, it makes a sine wave. It's just like 4D stuff. They always say, so impossible to even visualize 4D. 4D is a freaking movie, you moron. Okay, or an animation of something, you know what I mean? I think I can visualize a movie or an animation, you idiot. Why can't a grown adult that went to physics school for 8 years or 4 years, why can't they visualize 4D stuff when all it is a movie? Why can't they visualize duality when all it is a vibrating particle moving through space? Yeah. What is wrong with these grown adults, man? Why can't they visualize anything? Okay. And this is where your uncertainty principle comes into play. I just did that by memory. I don't know what the actual formula is. I know it's something close to this, right? I looked it up and Google says this one and this one, these are the correct ones. Mine should have 4 pi, not 2 pi. It should be greater than or equal, not less than. You know what I mean? This is wrong. These are right. The more you know the position, the less you're going to know the momentum. The more you know the momentum, the less, blah, 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 right? This is where, this is part of it. This is it, right here. See, let's say this electron, right? He's moving through space, right? And I want to take a picture of him, right? So I want to see where he's at, right? Right? Now, I'm going to throw a photon at him, right? Because I can't see electrons with my eyes, right? So I need to just like a camera, I'm going to throw photons on him, right? The photons bounce back, and the computer or whatever camera, displays it on something like a picture or a screen, right? So here's a red photon, right? The electron is going this way, right? But it's vibrating up and down. You can see its path up and down. And at this point right here, boom, the electron is right there where that red dot is. And that red dot is a photon. And they collide with each other, right? And then now I know where the photon is, or at least I where it was when I threw my photon at it, right? When I took my picture, the electron was right where that red dot was, right? So I have a good clear picture where that electron was when I took my picture, when I threw my photon at it, right? But look at it. Look at the path, okay? The path isn't a straight line going, from left to right, is it? No. The path that the electron takes is vibrating. It's going up and down, up and down. Now, I can't see this vibration, right? Like, look at these X's. What if, I don't know, did the photon hit the electron when it was there? There? I don't know. The physicist can't know where on this sine wave, the photon that we threw at it, where on the sine wave did the photon hit it? Because if you hit it here, right? You can plainly see the momentum is pointing this way, right? But what about that second X? What if you hit it at that X? Oh, well, now the momentum is this way. And what about the start? No, the momentum is this way now. So it all depends on where on that wave path of the particle particle electron is at. I need to know that to know this. That's why you get uncertainty, because you can't tell.